Hi everyone. Last talk for today. Are we ready for dinner soon? Okay, so I'm Zoe from the University of Melbourne, and today I'm going to talk about our paper, A Verified Cost Model for Call-by-Push Value Lambda Calculus, with my co-authors Johannes and Christine in this room as well. So I'm going to go through why we care about cost models and they are verified, and also introduce call-by-push value lambda calculus. So to start off, why do we care about cost models? I believe lots of people here are enthusiasts of functional programming. So functional programming languages, they are great for features of like they're able to describe things on a mathematical manner, and they skip the low-level details. Unlike imperative programming languages, they describe things on a high level, and this abstract nature makes them a great tool to reason about correctness of program properties. And as such, we care about functional programming. And when we think about functional programming, there are two things that we need to care about. One is being the correctness of our programs, and another one is the computational complexity of our programs, which is the cost. So in order to get the cost of functional programs, we have to get cost models for those programming languages. And this is where lambda calculus comes in. So lambda calculus is the basis of functional programming languages. As such, if we can get a cost model for lambda calculus, we can then develop things upon that for functional programming. So that's our motivation of our work for cost models. So next step is to introduce why we need to verify them, but everyone here is expert in verification. So I'm just going to introduce my prover. So I use her for everything for my formalization. And so now we'll give a quick recap of what lambda calculus is. So so lambda expression could be of three forms, one being the variable, the other one being the abstraction, and then the last one being the application. And how we evaluate in lambda calculus is using beta reduction. So this is one-step beta reduction where we carry out this application. We reduce this application by performing a substitution operation. So yeah, just a quick recap here. And another thing to notice in lambda calculus is the evaluation strategies. So there are two things. One is being whether we have weak reduction strategy or strong reduction strategy. So in the weak reduction, the reduction doesn't go under the abstractions. So inside the abstraction, we don't perform any beta reductions. And strong is the opposite. It does go down the abstraction. And then another thing is we have lots of different strategies specifying the order of beta reduction that we are carrying out. So the most popular ones being call by value, call by name, and call by need. So for call by value, we evaluate the function arguments first before we actually substitute them into the function calls. So the reduction happens first. And then we also have call by name, where it copies the whole function argument straight away into the function body without evaluating first, in which is like the evaluation is postponed. And then we also have call by need. It evaluates returns when needed. And it's similar to call by need, but it has memorization for variable sharing stuff. So as we can see that all these evaluation strategies will lead to very different cost models as they evaluate different parts first. So they will result in very different time and space costs. And this is when call by push value came to our attention. So call by push value is a variant of lambda calculus. And it has a special pair called the thunk and force pair, which allows the programmer to freely decide when they wish to evaluate which evaluation, in the sense that the evaluation order is actually defined within the program rather than on the meta level within the language. So yeah, our goal becomes to have a cost model for call by push value lambda calculus. And to explicitly define this cost model, we use the natural measure where we define the time cost to be the number of beta reductions and the space cost to be the size of the biggest intermediate terms. But once we have defined this cost model, how do we know that it is actually correct? What do we verify it against? So this is where Turing machines comes in. And Turing machine is another mode of computation that is equivalent to lambda calculus. And Turing machine is very straightforward when we're talking about the complexity of Turing machines. And it is used as a standard model for complexity analysis. So in this case, if we are able to find the relation between the cost model for Turing machines and call by push value lambda calculus, we can then show that we do have a valid cost model. So this is where the invariance thesis comes in. Excuse my pronunciation also for the rest of the paper whenever I talk about people's names. So by Slot and Van Emd Boas in 1984, they defined reasonable machines to simulate each other with polynomially bounded overhead in time and constant factor overhead in space. Furthermore, they also defined that Turing machines are reasonable. So in this sense, as long as we can show that our call by push value lambda calculus cost model has a polynomial time overhead and constant factor space overhead against Turing machines, we are then able to show that our call by push value lambda calculus is in fact reasonable. So there's prior work done for weak call by value lambda calculus by Forster, Kuzen, and Roth in 2020, where they showed that the weak call by value lambda calculus is in fact reasonable for both time and space. And in their paper, they went from Turing machines and via two abstract machines in the middle, including one substitution machine and one heap machine. They were able to show that weak call by value lambda calculus is in fact reasonable. And inspired by this, we also want to go through two abstract machines, including the substitution machine and the heap machine, to show that call by push value lambda calculus is reasonable. And so the first step was to formalize call by push value lambda calculus in Hope 4. And so this is the syntax for the call by push value that we formalized. So there's a few things to note here. First thing being the call by push value lambda calculus we are working on is the untyped version, and it's a subset of the call by push value lambda calculus defined by Paul Levi, where we are taking the core parts of call by push value. And also one more thing is that we are using De Bruijn index here for variables instead of XYZ variable names. So also it's defined using mutual recursive type in Hopeful. We can see there are two types, one being the value types and the other one being the computation types. And here we can see the thunk and force pair. They are the new constructors we have in call by push value comparing to regular lambda calculus. So this pair allows us to thunk the computation that we don't want to currently evaluate and use force later to enable these thunked computation to be evaluated again. And another thing that's different is that in this application here, the first argument is a computation and the second one is strictly a value, not a computation. And one more thing that might look a bit funky here is the p-seq. So p-seq does not exist in the standard call by push value. It's in fact something we added ourselves. It is equivalent to seq here. Actually, I should introduce seq. So Another thing is that it's not straight code for code, but also it's not straight code by push value definition from Polyvi. It's everything in this talk is kind of abstract notations that I used. That's easier to read, but also still using the same keywords that I use in my formalization. So the seek here essentially sequences two computations, and pseq is essentially two seeks together. But yeah, so it sequences two machines and put it result in a third machine here. Which I will explain why we need to add these a bit later in this talk, but just quick reminder here. Okay. And then the substitution function is pretty straightforward. Everything is just pushed down, recursive down. And then we define the big step semantics for call by push value. And yeah, just example here, if n evaluates to n prime, then the fourth thunk pair will in fact, fourth will cancel out thunk and also evaluate down to n prime. Yeah, similarly for pseq, we evaluate each argument first, and then we plug in the results from the first two machines, m to m1, into the third machine, n, and got the same result, n prime. And then we also embedded these big step semantics with time cost and space cost. So for the time cost, for instance, as I mentioned before, we use the natural measure, which is the number of beta reductions for time cost. So, wait, okay. So in this case, for example, for the fourth thunk example, m to m prime took k steps. So if we have extra fourth and thunk, we take it as k plus 2. And then in the pseq example, if each evaluation takes k1, k2, k3, then we have k1, k2, k3 plus 1 for this evaluation. And then for the space cost, still using the fourth thunk as an example here. For the space cost, we take the maximum intermediate term size. So in this case, it's either the biggest term that occurred during the evaluation from m to m prime, or it's the size of the original term with the fourth and thunk being there, which is why it's size of n plus 2. Okay, so now that we have defined everything for call by push value lambda calculus, next step is define, before we define abstract machines, we need to first define what inputs we can put into those machines. How do we compile our call by push value terms into machine readable programs? So we define program tokens as such, which is pretty much the same as what we have in the call by push value syntax, except we just added some T's to make them look different. And how the compilation actually works is like that. So basically we read in our call by push value term, and then we convert this tree structure term into a list structure, which is friendly for machines to read. And the compilation function for the substitution machine is essentially the same as the one we have for the heap machine, with just one thing being different here for the return constructor. And this was due to space cost issue with heap machine with the extra end red T there. But yeah, they're essentially the same thing, and we can unify them. But yeah, it's just some extra work, but it's pretty straightforward. Okay, so now that we have the compilation function, we can actually define the abstract machines. The first one being the substitution machine. So the substitution machine includes a task stack and a value stack. So pretty much following the reductions for the call by push value. And one example here being the reduction for variable case. So when we encounter a variable, it's a bit, okay, so when we see a variable on top of a task stack, we put this variable into the value stack straight away, and then we continue evaluating the rest of the programs. And yeah, we rolled out all the transition rules for the other cases as well. I'm not going to go through every single case here, but after that, we proved that this substitution machine can in fact simulate call by push value with the desired time and space bound. And after which we further formalized a heap machine. And heap machine is very similar. It has a task stack and a value stack, but on top of that, it has a heap as well. So in this case, heap machine is different that it doesn't eagerly substitute everything in straight away, but it actually puts the value onto the heap instead. As we can see that in the application case, when we have our function arguments here, we actually are putting them onto the heap here and updating the heap. And then we carry out the rest of the program. So similarly, the variable, the operation for variable will be different. So when we encounter a variable, we're actually looking up this variable value in the heap first. Then we put in the corresponding value into the value stack rather than put it straight onto the value stack. So similarly, we also formalize that heap machine can simulate call by push value with a desired time and space bound. Okay, so now we have formalized all these parts. What's left is from Turing machines to the rest of them. And this is in fact done by pen and paper. And how this works is, this is all the rules for the substitution machine. So how this works is that each reduction here can be represented by one Turing machine. So M1 here for one Turing machine can be encoded as one Turing machine, and then similarly we encode each reduction rules as separate Turing machines. And then overall, and then we can loop these machines to implement all the rules. And overall, we have this substitution machine representing the substitution machine. Similarly, we can construct a Turing machine representing the heap machine. And oh yeah, and this pen and paper proof is based on what's done by Foster, Coase, and Roth again in 2020. And we then use the alternating simulation strategy by alternating these two Turing machines, M-subt and M-heap. We were able to show that Turing machines can in fact simulate call by push value lambda calculus. So if we go back to the big picture again, we showed that Turing machine can simulate call by push value, but then there's actually still another direction that we need to show, which is from the call by push value to Turing machine, because the reasonable property requires the both ways simulation. So for the other direction, we actually chose to go through weak call by value lambda calculus here. So in this whole thing, so the left part has actually been done, as I mentioned before, Foster, Coase, and Roth showed in 2020 that weak call by value lambda calculus is reasonable, and this direction for us to do was from call by push value lambda calculus to weak call by value lambda calculus. And we formalized both the weak call by value lambda calculus and this simulation in HO4 as well. So we first defined weak call by value lambda calculus. variable application abstraction. And then we defined compilation function. So this compilation function is following the definition provided by Paul Levi from for call-by value and call-by push value in his thesis, except that we use pseek here instead of seek. So also just want to point out, we had to use pseek because of this part. So previously we used seek to begin with, but then it actually caused issue in the space cost part. So we have to revise our formalizations and add this pair property in order to avoid this issue. So yeah, similarly, we showed that we can in fact simulate weak call-by value using call-by push value within the desired time and space bound. And so yeah, so overall, we were able to show that both directions work. So call-by push value lambda calculus is reasonable. And I also have this graph in my paper. I think it's pretty nice to read. So the right-hand side is what we mechanized in this thesis. And the left-hand side is what we adapted from prior work. So yeah, I think that's everything. Any questions?